In this screencast, we'll continue our discussion of coding programs with Gӧdel numbers that we started in the previous screencast. So just to refresh our memory of what we were up to, let's say that we have an L program or a program written in some other programming language. We would like to compile that program. In theoretical computer science, sometimes the program compilation is referred to as coding, and if we're using Gӧdel numbers, its compiler is called Gӧdel coder. That Gӧdel coder produces a number, just one natural number, and that natural number will be given to the universal program that I hope we will discuss in later screencasts on this topic. Or that number can be given to another module program called Gødel decoder and or reverse compiler, and that will obtain the source of that program, the Gødel decoder. So for now, we will focus on in this screencast on Gødel coder. So the mainstream term is compilation for Gødel coding, and this is the Gødel decoder. Does what is known as a reversal compilation. So we're really talking about the foundations of mathematical theory of program compilation and reverse compilation. And universal program can be thought of as execution. So what this program does, it's an operating system or an interpreter. Interpretation would be another term that we can use. Okay. Just a reminder, a refresher, the Gødel number of a sequence of numbers. So let's say that we have a sequence of natural numbers, A1 through AN, AK. So Gødel number of the sequence, it is defined to be the square bracketed sequence A1 through AK, which is the product of the from 1 to k of the powers of primes, right? Corresponding primes. So the first prime will be raised to the power of a1, and then the second to the power of a2, and so forth. So for example, if we have the sequence 1, 2, 3, this corresponds to Gødel number of 1, 2, 3, and which is equal to 2 to the first, 3 to the second, times 3 to the 5 to the third. Okay, and so what's the Gødel number of the empty sequence? Well, it is defined to be 1. Why? Well, because no matter how many primes we raise to the power of 0, we're going to end up with 1. So just remember that we will use this fact later on in this screencast. So in the previous screencast, so we were talking about the first two tasks that the Gødel coder must accomplish. The first task is mapping variables and labels. So we have arranged the variables and labels into a sequences, and then so that every variable and every label of the L programming language is mapped to a unique natural number. The second subtask is mapping instructions to natural numbers, so coding instructions with natural numbers. So given a primitive instruction in the L programming language, we can compute a natural number uniquely corresponding to that instruction. And the third task, so with different colors that we will be talking in this screencast, the remainder of this screencast is mapping programs to numbers. Okay, so let P be an L program with some number of primitive instructions. So I1, I2, I3 program is a sequence of instructions, a linear sequence of instructions. I1, I2, IK, so all the way up to I, or down to ik, where k is less than or equal to 0. When k is 0, we have the empty program. I sub j, for j greater than or equal to 1 and less than or equal to k, is a primitive instruction. Right. Then the number of the program, the number of p, is defined to be the Gődel number of the individual instructions numbers. Right, the sequence of natural numbers corresponds to the individual instruction numbers. The number of instruction I1, then the number of instruction I2, the number of instruction I3, and all the way down to, or up to, however you want to say it, ik. So this is the exponent of the first prime. Okay, so it's the number of instruction I1, and so that's a Gődel number, right? And how do we compute those numbers? Well, by mapping variables and labels and by mapping instructions. So the first prime, which is 2, will be raised to that power. Okay. And so remember that this is a Gődel number. Right, and then the second prime, which is 3, will be raised to the number corresponding to the second instruction, and so forth. And then the prime, the kth prime, will be raised to the power of the kth instruction. And obviously this is all primitive recursive, because computing instruction numbers and computing Gődel numbers are primitive recursive. So y minus 1, right? Well, because if p is the empty program, in other words, k is equal to 0, the number of instructions is equal to 0, then the corresponding Gődel number, right, for the empty instruction sequence is this empty Gődel number. And by definition, it's equal to 1. Right? We reviewed this fact at the beginning of this screencast, and 1 minus 1 is equal to 0. So the number of the empty program is equal to 0, which makes logical sense. So let's go through an example. So let's take this program, A1. This is a label, x1 arrow x1 plus 1. Right, x1 equals x1 plus 1, we can read it like that. If x1 is not equal to 0, go to A1. This is an infinite loop, by the way, right? X1 keeps on being incremented, and so forth. So, but it doesn't really matter. The content of the program is of no concern to us. Our job is to compile this program, or give it to the Gődel coder and produce the Gődel number, the number of this program corresponding to this program. So we're going to take this p, give it to Gődel coder or to our compiler, and we will produce one natural number uniquely corresponding to that program. So and so this is our, let me use the C++ Java comment. So this is I1 instruction, the first instruction, and this is the second instruction. So by definition, the number of the program is the Gődel number, whose first component is the number of the first instruction, and whose second component is the number of the second instruction. So this is the Gődel number, and then minus 1. So the number of the first instruction, actually that was one of our examples in the previous screencast, and it's the pair of the pair. The first element is 1, the second element is the pair, also consisting of 1, 1. You can review our screencast on pairing functions. So what is 1? That's the number of the label, A1. And then the second component, this second one, is 1 because we're dealing with addition, and just by convention, any primitive instruction that does addition is mapped to 1. The type of that instruction maps to 1. This is just our convention. This one is the number of the variable used in the instruction, which is x1 and minus 1, and that's 2. And remember that the first variable in our list of variables or sequence of variables is y. So the number of x1 is 1, and then we subtract 1 from it and get 1. So the pairing function gives us 2 to the first 2 times the pair of 1, 1 plus 1 dot minus 1. And if you work it out, it's equal to 21. And if you work out the number of the second instruction, that comes out to be 46. Right, so you can work it out through the pairing functions and the labeling, and just watch the previous 2 screencasts on the theory of computation on Gődel numbers and pairing functions. So what's the number of this program? The number of this program is the Gődel number consisting of 21 and 46 minus 1. So that's 2 to the 21st times 3 to the 46 minus 1. That's a rather large number. But fortunately, if we were to implement it in a computer program, we could just implement Gődel numbers as simple sequences. We don't have to manipulate huge natural numbers.